Hello everybody, welcome. This is paper 2 from November 2024 and this is time zone 2. Let's have a look and see what we can do. Here we go, question 1. The following grid shows a restaurant's floor plan. There are 4 food stations centered at points A, B, C, and D. The Voronoi diagram for these 4 points is shown. Point A is not shown. 1 unit represents 1 meter. Point B is located at 2, 6. The equation of the perpendicular bisector of AB is y is equal to 4. First question, they're asking us to write down the coordinates of A. So we've got B, C, and D. They didn't include A, but it's enclosed within this site. They told us that this perpendicular bisector, y is equal to 4, is this horizontal line. So this dividing line between A and B is y is equal to 4. And they also told us the location of point B is 2, 6. X is equal to 2, y is equal to 6. Write down the coordinates of A. Simple 1-mark questions, so no process required. Remember, these perpendicular bisectors represent the points along which we are an equal distance between 2 sites. So every single point along here, we're an equal distance from C and D. Same here, every single point along this line right here, we're an equal distance from both B and D. We can use the same idea. If this is a horizontal line right here, and we would be an equal distance from both B and A. So that is where point A would be, and we can even write that in as 2, 2. So essentially an equal distance. Don't want to go over this too much, but remember, everything is a perpendicular bisector. This is the perpendicular bisector between A and B, and these are an equal distance as well. Alright, so coordinates of point A, let's write that as 2, 2. Points C and D are located at 9, 0 and 10, 6 respectively. So here we are at 9, 0, and then here we are at 10, 6. Find the coordinates of the midpoint of CD. That's part 1 of question B. And then part 2 asks us to find the equation of the perpendicular bisector of CD, and then to give your answer in the form of y equals mx plus c. Alright, so good IB question will often have you solve something as a scaffolding for something that follows, and that's exactly what they're doing here. So essentially we want to find the perpendicular bisector of CD. We're going to need the midpoint anyways to do that. So let's go ahead and find the midpoint of CD. So once again, here is C, here is D. Let's put in those coordinates as well, 9, 0 and 10, 6, just to make things a little clearer, I suppose. 9, 0 and 10, 6. And we're asked to find the perpendicular bisector. So once again, if we draw a point, a line segment connecting both C and D, we know that this distance is going to be equal to this distance, and there's going to be some point right in the middle that is the midpoint. Okay, so let's go ahead and find that. We can go into the formula booklet and actually find the midpoint formula. Here it is. I believe it's under, not under numbers and functions, but here, topic 2, functions. Where is it now? Our midpoint formula. Let's go all the way into, where's our midpoint formula? It's not with the slope. Here it is, right here. So right at the bottom, coordinates of the midpoint of a line segment. And essentially what it is, the average of the x values, the average of the y values, essentially the halfway point between 2 points on a line segment. So let's go ahead and write that out, and we'll solve it just in this corner right here. So the midpoint is going to be x1 plus x2 all over 2, and then we have y1 plus y2 over 2. And essentially the midpoint is the average of the x's, the average of the y's. So average of the x's, 9 plus 10 over 2, and the average of the y's is 0 plus 6 over 2. Let me clean that up. 0 over 6 over 2. This is going to be 19 over 2. You can use a calculator for this if you want, but halfway point is going to be 9.5, and then halfway point is going to be 3. And so we've got the coordinate of the midpoint right here, which is 9.5 and 3. And we can check if we weren't sure. Yeah, this looks about to be 9.5, and this looks to be about 3 if we wanted to double check. So there's the midpoint. And then the next question, they're asking us to find the equation of the perpendicular bisector of CD, and then give the answer in the form of this y equals mx plus b. All right. So we want the perpendicular bisector. What is the perpendicular bisector? Well, it's the line which itself is perpendicular, that is to say intersects at a right angle this line of CD. So this is the perpendicular bisector. Perpendicular because it intersects at a right angle. Bisector, bi is to, sect is cut, because it cuts this point exactly in 2 halves. So perpendicular bisector, we want to find the equation of this line. And we know an equation of a line is in the form of y equals mx plus b. So I'm actually just going to grab this because we'll need it later. I'm going to get a little more space to work this out. So let's put this back here. This was our midpoint. Maybe I'll go ahead and label that. And now we want to find the perpendicular bisector. Okay. So we're going to need to find an equation of y is equal to mx plus b. And for that, we're going to need to find the slope, and we're going to need to find the y-intercept. Since this is a perpendicular bisector, we know that the slope itself is going to be, well, perpendicular to this line. So the question is, what is the slope of this line? We can go ahead and look in the formula booklet and find our gradient formula, but I'm going to write it out here, and actually, let's just work from there. So slope is given by m, and we know it is equal to change in y. Actually, I'll remove these brackets. It's y2 minus y1, or change in y over change in x. So essentially rise over run. We can do this by solving triangles, but let's use a formula here. y2 minus y1, let's label these actually. This is x1 and, whoops, x1 and y1, and x2 and y2. Common question, does it matter with these labels, what we call x1 and y1 or x2? It doesn't actually, as long as you're consistent. So y2 is 0, y1 is 6, and we'll have x2 is 9, and x1 is 11. In this case, it might have actually been easier if we switched it around, but that's all right. Negative 6 over negative 1. Negatives, of course, negative divided by a negative will cancel out, and we'll just have 6 over 1, which is the same as 6. So we know our slope of a line is equal to 6. Okay, so what do we know? We know the slope of this line is equal to 6. Every single move to the right, we go up by 6. That's what the slope is saying. So how can we find this perpendicular line? That is to say, how can we find m perp? Well, what we can do is, if we look at this original, with this slope right here, just move it up just slightly, we can write this as 6 or 6 over 1. And remember, to find the perpendicular of some given slope, we can switch the top and the bottom, and then multiply by negative 1. So taking this 6 over 1, which is the same as just plain 6, it's going to be 1 over 6, and we're going to multiply by a negative. So we know the slope of this perpendicular line, m perp, is equal to negative 1 over 6. And that's what we're saying. Okay, and that does make sense. For every move to the right, we go down by 1/6. That's essentially what we're saying here. All right, so I'm actually going to take that, because that is, by and large, well, one of the other kind of key pieces of ingredients that we need here. So we found the slope, we found we found the perpendicular of this line. going to go ahead and cordon off some space. Yeah, that's fine. So, in the end, we wanted to find the equation of a line. So far, we have found the slope of this perpendicular bisector. So let's go ahead and work with that. We have y is equal to, we now know the slope is 1 over 6. 1 over 6x plus b. We don't yet know what this y-intercept is, though. If you go here, I mean, if we were to, let's say, extend this line all the way, what would it be? Roughly speaking, maybe it's, I don't know, 4.5 or so. But it's maybe not going to be the best practice. So this equation of this line, we're still missing b. But if we can substitute and find a point on the line, that is to say an x and a y value, then we'll move from having 1, 2, 3 unknowns to just one single unknown, and then we can solve. So we can find an x and a y on this line, on this perpendicular bisector. Oops. And if we substitute that into our equation, then we've got a point on a line, and we know if it's a point on the line, it satisfies and balances an equation. So if we have this point on a perpendicular bisector, substitute it in, and then we can find that last y-intercept. So in this case, what is the point on the line? Well, it's the midpoint. That's a value that is on the perpendicular bisector. So x is equal to 9.5, y is equal to 3. Let's substitute those values. X is equal to 9.5, and y is equal to 3. So substituting those in, negative 1 over 6, x is equal to 9.5, and now we moved from having 3 unknowns to just 1 unknown. And I think that looks good. So let's go ahead and work this out. And I guess we can end solve this. Algebra would be okay. We can solve this algebraically, but not too happy with the 9.5 multiplied by negative 1/6. So let's just go ahead and end solve this. Go into the calculator, menu, calculator, algebra, numerical solve. There we go. 3 is equal to negative 1/6 multiplied by 9.5 plus b, and solve for b. And the value is 4.58333. Let's see what it is as a fraction. Approximate the fraction, 55 over 12. I might actually just keep 4.58. I think that'll do. Negative 1.6 is not really good form to have fractions and decimals in the same equation. So potentially we could convert this negative 1/6 to a fraction, or we could take this 55 over 2. This 55 over 12. Maybe let's keep this as a fraction and write it all out as the same. Alright, so going back to the document, we found out that b was equal to 55 over 12. And so we have y is equal to negative 1 over 6 x plus 55 over 12. And this is an approximation to a fraction. In this case, that is actually the value, the exact value, 55 over 12. If you're unsure of using this approximation, you can just write it in decimals, and that should be fine as well. So I just want to bring up the mark scheme here. So here are the values that we can accept in the very end. Y is equal to negative 1/6 plus 6x plus 55 over 2, or we can write it to 3 sig figs as a decimal if we want. All right, let's go back to working out this question. Okay, actually maybe just before we do that, 6 marks. One of this is probably going to be, actually we can look at the mark scheme, but this is going to be midpoint formula. Let's actually just look at the mark scheme, I suppose. Here we go. Here they're just asking for the midpoint. Attempt to use midpoint formula as a method mark, and then the midpoint itself. Statement of slope, finding the reciprocal, that is to say showing negative 1 over 6, and then substituting, and then final equation of the line gives us the six total process marks. Okay, let's head back to the document. Okay. Customers in the restaurant take their food from the nearest food station. The following table shows the average wait time in minutes for each food station. So if you're at A, you have to wait 9 minutes. B, you have on average to wait 5 minutes, and so on and so on. Using nearest neighbor interpolation, find the average waiting time for a customer at point 46. So this might sound complex. Nearest neighbor interpolation, essentially they're saying, given that an individual is within one of these cells, that is to say if they're closest to A, B, or C, or D, how long do they need to wait? You know, if someone's going to food station A, they need to wait 9 minutes. B, it's 5 minutes, and so on. So let's look at this point 46, see which food station they're closest to, and we'll just use this table to determine how long they have to wait. So where is 46? 46, that would place this individual right here. Let's use green, I suppose. This is where they are, at point 46. And where would they go to? Well, they'd just go to this station right here. They're in this cell. They're going to go to B. And if they were to go to B, how long would they need to wait? They would need to wait 5 minutes. So, using the nearest neighbor, find the average wait time for customer. Just one mark question, so we can just write 5 minutes. Okay. The restaurant owner wishes to determine whether customers spend more money during the weekend. She decides to use a two-sample t-test at a 5% significance level. For this test, the null hypothesis is mu1 is equal to mu2. That is to say, average wait time is equal to average wait time during the weekdays is equal to average wait time. Sorry, not average wait time. Average amount of money spent is equal weekdays versus weekends. And that's always null hypothesis for a t-test, is mu1 is equal to mu2. Mu1 is the mean amount of money spent by all customers on weekdays, and mu2 is the mean amount of money spent by all customers on the weekends. State the alternative hypothesis. So alternative hypothesis is H1, and we're again relating mu1 and mu2. That is to say, mu1 is amount of time on weekdays, and mu2 is the amount spent by customers on weekends. Okay. And so what does this person want to do? They want to determine whether customers spend more, this is crucial, more money during the weekend. And so we said the weekend was mu2, so we want to see if mu2 is greater than mu1. Because mu1 is, well, the money spent on the weekday. Mu2 is the money spent on the weekend, and we want to see if customers spend more money during the weekend. Weekend is mu2. mu2 greater than mu1. All right. 1 mark question, so that's all they're expecting. The owner considers collecting her sample data from 2 weekdays and 1 weekend by recording the amount spent on the first 12 orders on each of these days. E1. State which one of the following methods best describes the owner's planned sampling. And we have the choice of convenient, systematic, or stratified. Remember, state is just a single answer. There's no justification needed. And of course, 2 mark question, this is 1 mark, and then we can say 1 mark here. All right, so we have convenient, systematic, or stratified. Let's just go over what these are. Convenience is you sample a population that is most readily available. That is to say, you wait by the turnstiles, and whoever is nearest, or whoever is most convenient to sample, this is who you sample. Systematic is a form of random sampling. This would be sampling every 5th person that walks in, every 10th person that walks in. That would be systematic, a form of random sampling where we select individuals at set intervals. Stratified is similar to quota sampling. Stratified sampling, we would want to break our overall population of concern, in this case customers, into stratum, or different strata rather. And in this case we would maybe want to break it up. We would say, okay, we want 40% people with families, and we want 20% seniors over 65, and we would break this up into strata or break it up according to proportions, and then we would perform random sampling within these strata. So once we determine the proportions, we would do random sampling within each of these strata. In this case, since this person is just recording the amount of time spent on the amount spent on the first 12 orders on each of these first days, this is actually just convenience. It's not random. It's just convenience in this case. So let's underline this. This is the sampling that she uses. State one disadvantage of this sampling method, or the sampling technique. Well, it's not random, and it being non-random, it is not representative. That is to say, we can't be sure that it's representative of the overall population. Maybe there's something to the first 12 people that come in. Maybe they're people that get up early. Maybe, I don't know, maybe they're elderly. Maybe there might be something to this population, the sample of these first 12 people that is not entirely representative of the whole. They might share some common characteristic which leads them to come early or be the first ones there, and this might bias our sampling. So it's not representative of the overall population. All right. The restaurant owner instead collects the data using simple random sampling. Okay, that's better. And the p-value is 0.0897 for the sampled data. State the conclusion for the test and justify your answer. Kind of an interesting question. They don't ask you to carry out the t-test, but we do have a p-value, and in order to determine whether we accept or reject the null hypothesis, we need to compare the p-value to our significance level. So let's look at p-crit and the p-value. So p-crit, or the critical value, and the p-value that we found. P-crit was 5%, or 0.05, and the p-value that we found, or that, I forget their name, but this person found, need to find it, I don't want to find it actually, that's fine. I'm half curious, but no, let's go, okay, fine. Maybe that's just a restaurant owner. Okay, never mind. Okay, here we go. P-crit and p-value. When we're comparing them, the p-value that we find right here of 0.0897 is greater than the p-critical value of 0.05. So our p-value is greater than p-crit. And what can we say in terms of accepting or rejecting the null hypothesis? A kind of nice rule of thumb, or a kind of rhyme, is if p is high, the null can fly. If p is low, the null has to go. In this case, the p-value is high, so we accept the null hypothesis. So in this case, we accept. More, I guess accurately, we can say that we fail to reject. Often in mark schemes, you'll see the examiners write condone. That means they're willing to let it slide in some sense if you say accept the null hypothesis. But better, we would say we fail to reject HO. We fail to reject the null hypothesis. So just to summarize what these values mean once again, the p-value is the probability that we see these results just based on chance. So if we're comparing the average amount of money that someone spends on the weekday versus weekends, we're going to see these kind of results just based on chance alone, roughly 8.9% of the time, roughly 9% of the time, which is somewhat unlikely, but it's not that level of assurance or guarantee that we would like in order to say something a little more definitely or concretely. It gives us some indication to believe that, yeah, maybe there is actually a difference in the amount that people spend, but it's not enough to pass or surpass our cutoff point. This is 0.05. This is the 5% chance. We want something less than a 5% chance that we see these results just based on chance alone. Because who knows, maybe it was, just due to random sampling that we see these kind of results. We're going to see these results roughly 9% of the time. It's unlikely, but not so unlikely that would lead us to reject the idea the averages are the same. All right, let's go on. Here we go. The Scheveningen Ferris wheel's lowest point is 8 meters above sea level, and its highest point is 45 meters above sea level. So here's 8 meters, this is 45 meters. Show that the radius of the Ferris wheel is 18.5 meters, and then calculate the circumference of the Ferris wheel. Okay, interesting question, only 2 marks, so we can go through it, I guess, fairly quickly. So here we are. They told us that the lowest point is 8 meters. So actually maybe we can write this in. The lowest point is 8, and the highest point is 45. This would mark out, well, the very, very bottom, and of course the very, very top. And if that is the case, what is the distance? We can say the diameter, I don't know how well that shows up, but the diameter of this would be, well, the distance between 8 and 45. In this case, that would be 37. Let's say the distance between 45 and 8 is going to be 37. But that's the diameter. We're looking for the radius. What do we know? We know that the diameter is equal to 2 radii. So the distance from the center to the edge is going to be half of this, going to be half of the diameter. So what we can take is the radius is equal to diameter divided by 2. Radius is equal to 37 over 2. Or we could say the radius is equal to, what would this be? This is 18.5. That would be our radius. We don't need to show all of that information. It's just a 2-mark question, so r is equal to 18.5. Should be enough. Just to summarize, distance from the highest to lowest, 8 to 45. We travel a distance of 37. That's the diameter, but the radius is just distance from center to the edge. So 37 divided by 2 would just be 18.5. Calculate the circumference of the Ferris wheel. So if we know our radius is equal to 18.5, circumference, we can find this in the formula booklet. Circumference is equal to 2 pi r, and I believe it should also be given in the formula booklet as pi times d. So we can solve this using either the radius or the diameter. Since we have the radius, let's use the radius. Circumference is equal to 2 times pi times 18.5, which is our radius. And they don't ask for the exact value, so we can write it out as a decimal. I'm going to work that out on the calculator that I have beside me right here. 2 pi times 18.5, and this would be 116.239 meters, or 116 meters to 3 sig figs. Alright, each of those are just 1 mark, so yeah, that's it, I guess. So not a lot of process is what they're asking for, I suppose. Here we go. There are pods equally spaced around the wheel that carry passengers. When the wheel rotates 10 degrees, find the distance that the pod travels along the circumference. Okay, this is actually a nice question, or at least I think it is. So let me just clear up some space and let's look at what they're talking about. Hopefully this red color shows up a little better. So they're telling us that the pods are spaced every 10 degrees. So here's, let's say, the center of the circle, and then here is distance from, we can use the pods, but let's use these spires. No, actually we need to use the pods because the spires don't actually line up. So here we go. There's this distance right here, and between, we can say the theta value, that doesn't show up too well, but we can say that the theta is equal to 10 degrees. Does this show up any better? Not really. Okay, theta is equal to 10 degrees. And the question is the distance that the pod travels along the circumference. So when the wheel rotates 10 degrees, find the distance the pod travels. So wheel rotates, we can imagine it rotates clockwise. Doesn't matter, but in this case we can imagine that it rotates clockwise. And if it's here and it rotates 10 degrees, what is the distance that it travels? So essentially, what is this curved distance that it travels? Okay, so essentially we know that if it were to travel 360 degrees, it would travel, well, the full length of the circumference of this Ferris wheel, which is 116. But it doesn't travel 360 degrees, it doesn't travel one full rotation, it only travels 10 degrees. And 10 degrees out of that full 360. So in this case, it's actually an arc length question. We can use the formula booklet for this. The arc length formula, let me see for B. The arc length formula is given by arc length is given by theta over 360 times 2 pi r. So remember, this once again is the circumference, and this is the fraction of the circle that we have. So in this case, we don't have a full 360, we just have 10 degrees out of a full 360, and then this is our circumference, is 2 pi r, which we actually found over here as 116. So this will give us the distance that the pod travels along the circumference. And for this, I'll go to the calculator and work it out. Okay, getting a new screen. Setting up a fraction, 10 over 360 multiplied by 2 pi, and then our radius was 18.5 originally. Okay, here we go. So it travels roughly 3.22886 meters. Okay, or 136 we could say of our total circumference, because it's just 10 over 360, 136 of our original circumference. Okay, let's go back to the document and write this out. 3.22886, or to 3 significant figures, 3.23, and let's include the units just in case. In this case, they don't ask for the units, but it's sometimes not entirely clear when they're required. Okay, let's go on. I think this is a really nice question. It transitions pretty naturally into a trigonometric function, and this is actually a question that's appeared a few times where we've had some kind of Ferris wheel. Actually was another Ferris wheel question on a past paper that linked it to trig functions. So it's been present before. Nice question, I think. So let's read this question and see what's going on more specifically. The height in meters above sea level of a particular pod is modeled by the function a sine bt plus d for a, b is greater than 0. So a is greater than 0, b is greater than 0, and this is height as a function of time. And time is measured in minutes. Okay, so we're going to need to find a eventually, but it doesn't actually ask us to, but we need it for this equation. It asks us to find b and d, and the information that it gives is some distance information above, and then this fact that the wheel takes 15 minutes to complete one revolution. So let's actually go and find a, b, and d for all of these points, or sorry, a, b, and d for each of these parameters, or these variables, I guess. Okay, so shall we start with b, or let's start with a. Usually we do start with a. Not sure if we can begin with a graph. So I'm going to Actually, I will draw kind of just representation of what's going on here. So here's the Ferris wheel, and let's imagine we choose some point, some kind of point. They tell us it's a sine function. So in this case, we'll imagine that this is the pod that we're talking about, and we want to track the pod through height. And as this pod circles, do they tell us if this goes, so actually it doesn't tell us exactly that this goes counterclockwise, or sorry, clockwise or counterclockwise, but in order for this to be a sine function, it actually needs to go counterclockwise. But we can leave that aside for now. So there's this Ferris wheel, and let's call this line right here sea level. So this is sea level right here, and we know that this is 8 meters above sea level, this lowest point right here, and then we also knew that this point right above here was, I think it was 45 meters above sea level. So if we go, we can write this out here. This was 45 meters above sea level. Let's see if we can do something like this. All right, this is 45 meters off the ground, and here we go, 45 meters above sea level. Okay, so what happens as this thing sweeps through time? Let's imagine we set up some coordinate axes, and we'll try to model what is going on here. And we'll set this as equal to 0, just like this is sea level. So this y-axis is the height above sea level, and then this axis right here we'll call t. Actually, it's the time. We can even erase this and call this h of t, because that's what it is. So if we're imagining we're starting at this point right here, which is the height of one of the pods at the very, very beginning, then what do we have? The pod at the very, very beginning is going to be halfway between here. Let's work out the numbers in just a little bit. Let's just get some kind of conceptual understanding first. So here's the pod, it starts here, and then as it rotates, it's going to increase in height as time passes. And here it is, it's going to then decrease in height after it reaches its highest point. It's going to come to that starting point again, and it's going to go down and down and down and down, all the way to its lowest point, and then it's going to come up again and go back to its starting point. And it's going to do this again and again and again and again in this sinusoidal manner. So let's imagine that this is the starting point. Let's maybe draw this horizontal line. Let's say this is a horizontal line upon which it, what can we say, oscillates. And let's go ahead and draw the height through time in some kind of rough way. So here it is, it starts at this midpoint, and then if it takes 15 minutes altogether, we'll work out the numbers in just a bit, but we see it as it goes through here, it's going to increase, decrease, decrease, and then increase. So let's try to map that out. So here it is, it goes up, and then down, and then up, and then down, and so on and so on and so on. And this is its height through time, going up, then down, up, then down, up, and down, and so on and so on. So it does actually make this oscillating pattern. Okay, now let's find A, B, and D. I'm going to find A first, just because it's usually the easiest. A, we know, is equal to, and this isn't given in our formula booklet, and I'm not actually sure this is actually the best way to work it out, but this is the way it's often taught. It's max minus min over 2. That is to say, the highest point reached in the wave, in this case the highest point is equal to 45, and the lowest point is equal to 8. It's max minus min over 2. So the highest point we reach is 45, the lowest point we reach is 8, and then we divide by 2. And this actually looks a lot like the radius, and I guess that's not entirely an accident. And this is 18.5. Another way to work this out is if we know what the midline is, this value of A is just the height of a wave. So essentially, if our highest point is 45 and our lowest point is 8, we travel through a distance of, we said it was 37 last time, so halfway from this midpoint to the top would be, well, half of that 37, which is 18.5. So that's the value of A. We're going to need that later. Let's find the value of B. That's what it's asking as well. So let's save this and put it here, I suppose, for now. And let's find B. B is equal to, so B is the number of oscillations in 360, in this case minutes, or 360 degrees, we would say. What makes it challenging is it's not in the formula booklet, but B is equal to 360 over the period. And the period, remember, is the time taken for one complete cycle. For one cycle. So in this case, we have 360 over the time taken for one complete cycle is 15. 360 over 15. This is going to be equal to 360 over 15 is equal to 24. There we are. So there's our value of B. And the value of D, here we go. Actually, let me just label these so we don't forget. The value of D right here, this value of D that is all by itself is the vertical shift. And it tells us, usually our sine wave is right along this x-axis right here. It oscillates and then it goes under and then it goes up. But in this case, for real life situations, we often want to shift this up or down. And the value of D is actually just the value that we shift it up by. There is a formula for this, and we can use it. We can actually erase this and condense things. We can find the formula. Put this away right here. I think that's fine. For D, it is max plus min over 2. Essentially, this is the value of D. It's the horizontal value through which we oscillate. So the value of D is this right here. And it's the average of its highest point and its lowest point. Or, essentially, after you found A, you can always say, okay, if this is our lowest point, we know we have to travel a distance up to get to that midline, or a distance down to get to that midline. That will also work if we want. Let's use max plus min. This is 45 plus 8 over 2, or this is going to be 53 over 2, which is going to be 26.5 meters. Just to do another check, let's use this method right here. 8 is at our lowest point. Let's travel a distance of A, which we know is just the height of the wave, 18.5, which will give us again 26.5, which is correct. Okay, good. So we've got the values of A, B, and D. Now let's go ahead and write down the equation of the sinusoidal function. And not too much space, so we'll box it in here. Okay, so we've got h of t is equal to A, we said was 18.5. Sine is just our function. B we said was 24t, and this is plus 26.5. A lot of space. And make it work. Okay. So there it is. Here's our value of A, here's our value of B, and then our value of D. 18.5 sine 24t plus 26.5. Great. Let's go on to part D. Use the model to find the values of t when the height of this pod is 33 meters above sea level for when t is greater than or equal to 0 and less than or equal to 15. So we know it takes 15 minutes to go through one revolution. Essentially what they're asking is, how long is this pod above a height of 33 meters given one revolution of 15 minutes? So to put that into context, I'll try to clear this up just a little. That'll do. Okay. So, I don't know if I can take this. No. Okay. Alright, so if we have this height, and we said, just as a reference, this was 26.5. This is our midline. If we have this question of when is this thing, or for how long is this Ferris wheel above this height of 33 meters, essentially what we're asking is, if this is 33 meters up here, given one time of a full revolution, which means we're starting at, let's say, this is our starting point, and this would be our ending point, for what length of time are we above this value of 33? And then in a real-world context, I suppose, here's the Ferris wheel. It goes around. For what length of time is it above this point of 33? And so that's the question. If we can find t1 and t2, well, this distance itself is just going to be t2 minus t1. And that should be that. So let's find these points of intersection, and let's work it out. So I'm going to show you two different ways on how to solve this. Let's go to the graphing calculator. Here we go. Let's graph the function 18.5 sine, and 24, we need to use x, plus 26.5. It doesn't show up. Let's zoom out and see where this is. Okay, that's not bad. I'm going to condense the x-axis just a little. X we'll put to maybe, we only need 15, right, from 0 to 15, so let's maybe put negative 5 here, and then just put maybe 25. That'll give us more than a wave, but it should be okay. Okay, so here's our function. This is height against time. Let's draw another function, graph entry function, and then let's put that height of 33. So they want to see how long is it above this height of 33. So this is the first time it's above 33, and then it stays above for a certain length of time, and now it goes under. So let's see the first time it goes above. So using intersection, okay, at 0.857 minutes. And let's find the other point at which it is no longer above this point. 6.6429. Okay. Nice kind of visual representation. And so after 0.857 minutes, it's above, and it stays above for a certain while. And after 6.64 minutes from the starting point, it's no longer. So what's this time in between? Let's go back to the document and work this out. So here it is, part D. We know that the first time it was above 33 meters was at 0.857, let's put full sig figs, 08. And then it was no longer above 33 at this point of 6.6429. So once again, here's this one point, here's the other point. We take the second point, subtract this first point right here, and it will give us this t2 minus t1. It'll give us the length between the time it was first above and then when it was no longer above. So I don't know if we really need to write out so many steps, but t2 minus t1, which is equal to 6.6429 minus 0.85708. And I'm actually going to work that out on the calculator that I have beside me. 6.6429 minus 0.85708. And the total length of time is 5.78582, or to 3 sig figs, 5.79. Okay. So, why did I keep so many sig figs? Ideally, you want to only round to 3 sig figs, or 3 significant figures, once you've reached the end of a question. During the question and the intermediate steps, you want to save as much accuracy as possible. So this 5.785, if we had cut off to 3 sig figs, we would have actually had a different answer in the end. So that is important. Oh, actually, sorry, all of that is true. All of that is true. But if I can just highlight this question once again, it says use the model to find the values of t when the height of the pod is 33 meters above sea level for for when t is greater than 0 and t is less than 15. So actually all we needed to do was find these values. So in this case, we didn't actually need to find the total time that it's above. That was my assumption, maybe because it's a common kind of question, but in this case we actually just need to find the times at which it first reaches this value and when it reaches this cutoff point of 33 once again. So that's it actually, we just need this and this. I'm going to go ahead and erase this actually. And we can round these values to 3 sig figs. Okay, let's go to this final part of this question. Since the Ferris wheel opened, it has been operating for 3,000 days, and each day it rotates non-stop for 8 hours. Calculate the total number of revolutions that the Ferris wheel has made. Give your answer in the form of a times 10 to the k, where a is greater than or equal to 1, less than 10, and k is an integer. This notation sometimes confuses students, but this is just scientific notation. This is some value between 1 and 10, but less than 10, times 10 raised to the power of k. So some integer value, it's not an integer value, some decimal place with how many zeros, and then the k would tell us how many zeros come out after that. It's a way to condense a lot of values, especially if the numbers are very big or very small. Okay, so let's go through part E. Calculate the total number of revolutions that the Ferris wheel have made. Okay, so what do we know? We know that it rotates 8 hours a day non-stop and 3,000 days. So how many hours has it been rotating for? Well, if it's rotating 3,000 days times 8 hours, well, it has been rotating 8, 16, 24. It has been rotating 24,000 hours. So I'm not sure that I need to write this, but this is days, this is hours. So 8 hours a day for 3,000 days, we have 24,000 hours, and we want to know the number of total revolutions. And going back up here, tells us that it takes 15 minutes to complete one revolution. So how many revolutions can we make in 1 hour? I guess we can write that out here. So revolutions per hour. Well, in this case, we can make 15 revolutions. We can make 1 revolution every 15 minutes. And I don't know if we need this kind of level of maybe detail, but we know 15 minutes is 1/4 of an hour. And so how many revolutions can we fit into 1 hour? Well, 1 revolution fits into a quarter of an hour. That means we can fit in 4 revolutions. 4 revolutions per hour. That's how many we can, I guess, go through, I suppose, in an hour. And that would be it. So 24,000 hours, 4 revolutions per hour. Let's go ahead and multiply this. We can actually do something kind of clever. Let's write this out. 24,000 hours times 4 revolutions per hour. And this is actually kind of neat, not really needed, but our units actually cancel out. And then we would be left with 24 times 4, which is 96,000 revolutions. Okay, but we want to write it in scientific notation, so we want some value of a that's greater than or equal to 1, less than or equal to 10. Here's our decimal point. Let's go 1, 2, 3, 4 hops to the right, or sorry, to the left, to write this as 9.6, and it's times 10 to the, and we just had these 4 hops right here, and so that is going to be times 10 to the 4. Essentially, we're condensing 1, 2, 3, 4 zeros. And that would be our answer, 9.6 times 10 to the 4 revolutions. Great. Okay, pretty decent exam so far. Let's go to question 3. A survey was answered by 20,000 expatriates, people living in country that is not their own. The data ranked countries in order of the country they felt was best for expatriates. The highest ranked country was Switzerland. These results were compared to happiness scores taken from the World of Happiness report in 2022. The following table shows this data for the top 10 expatriate countries. Here we go. So Switzerland ranks number 1, New Zealand 2, Spain 3, and so on, so on, so on. And these are the relative happiness scores in each of these corresponding countries. Okay. For the happiness score, that means this row right here, find the upper quartile and the interquartile range. And this is a 4-mark question. So finding the upper quartile would be a mark itself. Interquartile range, we would need the lower quartile as well. And then we would need to do some calculations for that. IQR, remember, is equal to IQR is equal to Q3 minus Q1. So let's go ahead and find these values. We could actually arrange these happiness scores, and we could do it that way, find 25% and then the 75th percent, given that we have 10 values. I think actually it will be easier to work these out on a calculator, and that's what I'm going to do. So let's go to the calculator here. Go into spreadsheets. Let's just use one variable, statistics, and let's put those happiness scores in. 7.5, 7.2, 6.5, and so on. So these are just the happiness scores. 7.0, 6.6, 6.7, and 7.4. Okay, just going to go up once again, make sure that these are all correct. 7.2, 6.2, 6.7, and 7.4. Okay, so here are our 10 happiness scores. Let's go menu, statistics, stat calculations rather, and we just got one variable. It's just the happiness scores that we're considering, and we put them in column X. All right, there's Q1 and there is Q3. So our upper quartile is 7.2 and our lower quartile is 6.5. Let's go ahead and return to the document here. Upper quartile Q3 is equal to 7.2, and the interquartile range is right here, and this is Q3 minus Q1. On the calculator we found that Q3 was 7.2, Q1 was itself 6.5, and in this case our interquartile range would be 0.7. Alright, not too bad. I was wondering initially whether there was something else expected for these 4 marks, but here is a look at the mark scheme. Q3 has 2 answers awarded just for the answer. We have a process mark here of Q1 and then calculation of interquartile range. This is all actually Q1. I guess we assume this right here in order to calculate IQR and then answer. So a lot of marks actually for something which seems to be pretty straightforward. Maybe it's a little generous, but there it is. Okay, part B. Show that Switzerland's happiness score is not an outlier for this data. So here's Switzerland's happiness score. It's 7.5. So how do we determine whether something is an outlier or not? I'm going to draw a quick box plot to just provide some intuition, I suppose. So in this case, we know the upper quartile was 7.2. The lower quartile was 6.5. I'm actually just looking at this document as well. And it said that the median, we don't need this, but the median was equal to 6.85. And the question is, okay, well, we've got some whiskers as well for this box plot. Here we go. And maybe the whiskers are up to here. And the question is, like, how far could these whiskers, at least in theory, extend? I mean, it starts to look ridiculous if they extended all the way up to here. There would be a happiness score of 10. That might be an outlier. But the question is, like, how far can these whiskers extend? Or put another way, how far does a data point need to lie outside of the main cluster of data points for it to be considered an outlier, a data point that lies too far outside of this main cluster? And so the question is, how long do these whiskers extend? Well, the whiskers extend. Here's Q3, here's Q1. The whiskers will extend 1.5 times IQR above Q3, and similarly 1.5 times IQR below Q1. Anything beyond this cutoff point is an outlier. Anything beyond this cutoff point again is an outlier. So let's go ahead and see whether, or justify, prove that this is not an outlier. Okay, so our formula in the end is Q3 plus 1.5 times IQR. Q3 we know is 7.2. 1.5 IQR we found was 0.7. Let's go ahead and work that out. 1.5 times 0.7. This is equal to 1.05 plus 7.2. And this, in the end, is going to be 8.25. So essentially the distance of this is going to be 1.05, and that's the extent to which these whiskers can extend. Anything beyond this point of 8.25 becomes an outlier. Anything not beyond this point, well, we just extend these whiskers to meet it. Since Switzerland's value, its happiness value, is only 7.5, what we could say is that 7.5 is less than 8.25, and therefore, fancy if you want, therefore not an outlier. Alright, and that would be that. Okay, let's go on. Here we go. The happiness scores were ranked to calculate Spearman's rank correlation coefficient, RS. These ranks are shown in the following table. Okay. So here we have, again, the happiness scores, and then we're ranking them. And it looks like we're ranking them from highest to lowest. Write down the value of A. Okay. So Switzerland has the highest happiness, and then is there anybody else after? Yes, the Netherlands. And then after this, it looks like New Zealand and Australia. And the question is, okay, well, do we just go random? Do they both share, 3? Do they both share 4? Well, if we were to rank these things, they would both share the 3rd and 4th ranks. We can't both give them 3. We can't give them both 4. So what we do is we take the average of the two. And in this case, they would share this value of 3.5 and 3.5. So once again, here is the highest, this is the second highest, this is the third, and oops, it is not the third and the fourth value. Sorry, this belongs to Australia, which is the third and fourth value. Oops, not 3.5. Here we are. So here's the first value once again, the second highest happiness rank, and here is Spain, or sorry, not Spain, New Zealand and Australia, both sharing the third and the fourth rank. They can't both be third, they can't both be fourth. They share that distinction of the 3.5th rank, I guess. First, second, this is the third and the fourth. We continue counting. This is the fifth, sixth, seventh, and then right after that would be the eighth. And it doesn't look like anybody is sharing that, so this would just be the eighth. Let's put those values in. A is equal to 3.5. B was equal to 8. And C was itself equal to 3.5 as well. Okay, find RS. Remember RS, R is correlation, R sub S is Spearman. So let's go ahead and find Spearman. Let's go to the calculator when you get a new document and go into spreadsheets. Remember, for Spearman, we just put the ranks in one column and the happiness scores in the other. You just want to see if there is a correlation between the rankings of the happiness score and find RS. So we want to compare the happiness scores, the ranks of the happiness scores, and sorry, I'm back in the document here, the expatriate countries rank. So kind of a nice kind of trick question, not a trick question, but in some sense. So we can't directly compare the happiness rank with the happiness score. That's not what a Spearman correlation does exactly. It compares ranks and ranks. So instead of directly comparing the happiness score with the country rank, what we're doing is we're comparing ranks with rank. That is to say, the happiness ranks with the expatriate country ranks. And they are lined up. This is Switzerland in the first column, and this is Switzerland in the second. So we should be able to use the same order. So let's put the ranks for expatriate country in, and then we'll put the ranks for the happiness in the other column. So here we go. Let's go to the calculator once again. Expatriate country rank, these were already listed as 1, 2, 3, all the way up to 10. And these happiness ranks, for Switzerland first, Switzerland was ranked as the happiest, and then we have New Zealand at 3.5, and so on. 9, 10, 5, 7, 6, 2. Okay, just make sure these values are correct. 5, 8, 3, 5, 9, 10, 5, 7, 6, 2. Good. So we're comparing ranks and ranks. That's what Spearman does. Here we go. Statistics, stat calculations. In this case, we've got two variables. We've got happiness and expatriate rank. X's with an X, Y with an Y. Let's go ahead, and essentially what we've done is we've run a correlation, but not on the data itself. We've run it on the rank data. And here it is. R is equal to 0.164. So let's go back to the document. RS, Spearman correlation, is equal to 0.164. Alright, and that's actually pretty low correlation between the two. Okay, moving on. If France's happiness score is upgraded to 6.9, whereas France, this is France right here, Explain why the value of RS does not change. This is a common question as well. Here's France. It's ranked 6 in terms of its happiness score. If it moves up to 6.9, for example, why does the rank not change? Well, it's ranked 6 right now. It can go up to 6.9, but it's still not happier than Ireland, for example. So in this case, it could increase up to 6.9, but the ranking wouldn't change. So explain why RS does not change. Well, why? Because rank does not change. So it would still have the 6th rank. All right. Joe concludes from this data that countries with high happiness scores are likely to be favorite expatriate countries. State with a reason whether Jose's conclusion is appropriate. So 1-mark question, is there a link between the high happiness scores and favorite expatriate countries? Well, our correlation is actually pretty low. Why? State with a reason whether Jose's conclusion is appropriate. We would say it's actually not appropriate because RS is low. RS is equal to 0.164. That would be all we would need for a 1-mark question. I would say one thing to potentially be mindful of, and sometimes students do this, is they write really, really long kind of paragraphs or long kind of explanatory sentences, hoping that, there's something in there that the examiner will like. And maybe, I'm not sure, I don't think it's maybe the best strategy, but something short. If you have a good idea of what the answer they're looking for, well, correlation is low. RS equals 0.164, not appropriate. And that's all the examiners would look for. All right, question 4. Sweets are sold in cylindrical containers. A new label for the container is being considered. The label will be a rectangle that is 5 centimeters wide and 9 centimeters high. The design of the label is a curve as shown on the following axes, where 1 unit represents 1 centimeter for both axes. So here we have the width and the height, and this is going to wrap around some cylindrical, you can imagine like a Coke can or something like that. The values in the table approximate points on the curve correct to 1 decimal place. Here is width and then the corresponding value of height. So for example, when x is 0, y is equal to 4. When x is equal to 1, y is equal to 7.3, and so on. Use a trapezoid rule with 5 intervals and the values given in the table to estimate the shaded area below the curve. Okay, so 3-mark question. Trapezoid rule seems like a fairly straightforward kind of application of trapezoid rule. Just to go over what the trapezoid rule is once again, here we're going to use 5 intervals. So we'll see how many trapezoids that results in. This would be 5 trapezoids. But what does the trapezoid rule do? It approximates the area under the curve using trapezoids. So I'm going to draw a few lines here, just connecting the heights at each of these points, and then just draw out just in a little more detail what the trapezoid rule does. And then here's 5 right here. So what the trapezoid rule is, usually we draw our trapezoids like this, for example, maybe with the straight line, of course. And this would be one of the horizontal side lengths. This is the other horizontal side length. And then we have the height of the trapezoid itself. Here we're actually rotating the trapezoids 90 degrees, and we have our trapezoids like this. But we still have this horizontal, which is now our vertical kind of parallel side lengths. And we have this height, which is now essentially our width or the base of these trapezoids. And so what we're going to do is we're going to use a set of trapezoids to approximate the area under a curve. And so obviously this is a little better than rectangles. It doesn't give us 100% approximation, but this is the idea. If we find the area of each of these individual trapezoids each of these 1, 2, 3, 4, 5 trapezoids, then we can approximate, roughly speaking, the area under the curve of this function right here. So what is our trapezoid rule? I'm going to go into the formula booklet and just bring this up once again. Let's go into calculus. Oops, wrong one. Here we go. This is our trapezoid rule. Have some other videos kind of explaining this in more detail, but just once again, this is the integral, and this is saying the sum of all the tiny little, in this case it's actually rectangles, all the tiny little rectangles under the curve with a starting point A, ending point Y of some function can be approximated by, and then this is our trapezoid rule. Oops, this is our trapezoid rule right here. So you don't actually need this part right here. This is just the kind of explanation at the beginning. They're telling us that it's an approximation. The trapezoid rule can be used as an approximation. But what is the trapezoid rule itself? Well, we have this half h. H, we do have a formula for h. This is the endpoint minus beginning over total number of trapezoids. I think it's easier actually to consider h as the width, or in this case the base of the trapezoid. So 1/2 h. This is the height of the starting point plus the height at the last point, and then we have 2 times all of those intermediary points. It looks kind of complex, kind of intimidating, but it's actually not that bad once you get a little familiarity. So let's go ahead, go back to the document and work this out. So I'm going to work this out. We're on the, I guess on the right side, so I'll move this over here. Don't think we need that for now. And let's write out the trapezoid rule. So we don't need to show this, but I guess I will. There's the area under the curve, starting point A, ending point B of some function can be approximated by, and then our trapezoid rule. So I'll move this. Actually, I'm going to just delete this. But this is essentially what we're saying. We're approximating the area under the curve. And so how are we doing that? It's 1/2 h. And we're going to open up some brackets. Going to open up a big set of brackets because we actually want to multiply everything by 1/2 h. But we're going to multiply first by y0, that initial starting point, yn, that final starting point, and then we're going to have 2 times y1 plus y2 plus all the way up to everything up to yn minus 1. Nth is the last one, n minus 1 is everything up to the very end. Okay, and there's other videos showing the trapezoid rule, but why do we have the first and the last just multiplied by once? Well, because the first and the last they're only part of the area, well, one time, whereas these intermediate values are shared by this trapezoid right here and this trapezoid, and same with these 2 intermediate values and these intermediate values, and so we multiply them by twice because these side lengths are shared between 2 trapezoids. That's maybe a brief kind of cursory explanation, but there are other kind of videos that go into it in a little more detail if you need. Okay, so let's go ahead and apply this. 1/2 h. So what is h? We can use the formula for h that they give us, h being equal to b minus a over n. Remember, b is the endpoint, a is the starting point, n is total number of trapezoids. And this would be ending point is 5, starting point is 0, over, here we have 5 trapezoids, over 5, and that gives us a value of 1. That's one way to do it. The other way, I think that's a little more straightforward, is to say that h refers to the width of the trapezoids, and we can see that, well, the width is just 1. 5 trapezoids spanning a length from 0 to 5, the width of each of them will be 1. And there it is. The h actually comes from the height of our trapezoid when it's laid on its side, I suppose. Since we're flipping the orientation, the h becomes the width of the trapezoids. So 1/2 times 1. Open up some brackets, and we want to take the starting point and the ending point. Starting point is 0. The height of the starting point, this first value right here, is 4. And the height at the end is 0.7. Right here is 0.7. That's the height of this trapezoid. Plus 2 times all of the intermediate heights. And the intermediate values are 1, 2, 3, and 4. So what we can do is we can take these intermediate heights of 7.3, 6.7, and so on. So, try to get both on the screen. 7.3 plus 6.7 plus 4.0 plus 1.3. And then we'll close those brackets. Make sure you have brackets here, because we want to multiply 1.5, or 1/2, by everything in here. Okay, and there is our approximation for the area under the curve. Let's go into the calculator and work this out. So, calculator, we'll take 1/2, multiply by 1. We don't really need that because it stays the same. And then let's get those two brackets. So 4 plus 0.7 plus, and why we have two brackets is because we want this to be multiplied by everything on the inside. 2 times 7.3 plus 6.7 and so on. 1.3 being the second last height. Just checking to see if that's all good. Looks good, brackets are appropriate, and there is our approximation. 21.65, and in this case it would be cubic, or sorry, not cubic, but square centimeters. So let's go back up to the document, and we can say the approximation is equal to 21.65 centimeters squared to 3 significant figures. That would be 21.7 centimeters squared. Okay, and there's our approximation. The curve used in the label design can be modeled by y equals x cubed over 3 minus 3x squared plus 6x plus 4 on the interval where x is greater than or equal to 0 and less than 5. So here's this function. Write down the integral that represents the area of the shaded region, and then the second part, it says, hence, find the area of the shaded region. Nice 4-mark question if we're familiar with these things. So remember, the area under the curve can be represented by this summation. So this is the sum. The sum from what? Well, our starting point A to our ending point B of some function, f of x dx. dx is just the tiny little changes in x. And essentially what this does, maybe this is not entirely needed, but here it is. If you've got some function like this, what this is doing, it's taking the sum of all the infinitesimally small kind of squares, or rectangles rather, oriented along the x-axis, where this is just the tiniest little bit dx. And it's taking an infinite number of these little rectangles, and it's summing them all together. And that's what our integral actually does. So, if this is the case, we have the sum with some starting point A and ending point B of some function in regards to dx. Let's go ahead and work that out and just substitute those values. So the sum with a starting point of 0 going all the way to 5, 0 going all the way to 5 right here. Our function itself, we can just write it in as x cubed over 3 minus 3x squared plus 6x plus 4, all in regards or in relation to dx. And that's really it, actually. That's our integral. Starting point, ending point of some function, and then what's our variable? We just relate it to dx. And now find the area of the shaded region. We just need to put that into the calculator. So let's go back to the calculator and work this out. Let's go Menu, Calculus, and we want to find the numerical integral. Okay, starting point of 0, going up to 5. Our function, set up a fraction, minus, and then we should be okay here. 3x squared plus 6x plus 4, all in relation to dx. I'm going to check to make sure that is indeed the function and everything is good. Alright, and this should be reassuring as well. If they were drastically different, then say, geez, one of these may be wrong. Alright, our area is 22.08 centimeters squared. So I'm going to go ahead and write this in the document. Equals 22.08, and I guess 2 sig figs, it would be 22.1. Once again, this is centimeters squared. Alright, I just looked at the mark scheme to see whether units were required, and they aren't. They aren't required here in this case, but in some cases units are required, and to be honest, it's somewhat unclear how to tell. So sometimes not a bad idea to include them. Alright, continuing on with question 4. The sweets are sold in closed cylindrical containers with radius r and height h. The whole container is made from one type of material, and it's assumed that the thickness of the material is negligible. Each container has a volume of 600 cubic centimeters. Write down an equation in terms of r and h that shows this information. So an equation, we're relating two values. In this case, we know the volume and we know the radius and the height. So what is the volume of a cylinder? A cylinder, just like anything with what's called a uniform cross-section, we have the base. If we find the area of the base and then multiply by the height, or just its extension in whatever direction the uniform cross-section is, like if we cut a circle through here, we have the same uniform cross-section. If we find the area of the base, multiply by the extension, then we can find the amount of space that this takes up, which is another word for the volume. So let's go ahead and do that. We know the volume of a cylinder is given by, well, area of the base is pi r squared. This is actually in the formula booklet as well. Pi r squared, and then the height itself is just our extension. So volume of a cylinder is pi r squared times h, and in this case the volume is equal to 600 centimeters cubed. So we've got 600 centimeters cubed is equal to pi r squared times h, and it's just a 1-mark question, so that looks pretty good. Alright. The amount of material used for each container can be modeled by the external surface area of the container. The external surface area A of the container can be expressed as, so this is the area is equal to 2 pi r squared plus k over r, where r is greater than 0. Find the value of k. Okay, interesting question, 4 marks, so it's going to be somewhat involved. Let's go ahead and see what we can do. Maybe we'll write it in this space here. Okay, so they're telling us that the external surface A can be expressed by this equation right here. And the external surface of the cylinder is going to be this outside surface right here. So essentially this wrapping, this horizontal wrapping. And we're also going to have both of these faces, this circular face here and this circular face here. So essentially what we have is the surface area, the external wrapping, is equivalent to the surface area of this cylinder. So what is the surface area of our cylinder? You can go to the formula booklet and find that out. Geometry and trigonometry. And we can go down and look at area of the curved surface of a cylinder is 2 pi r(h). But I think, is there the area of the curved surface? Okay, so it just gives us the area of the curved surface, which is okay actually. We can work with that. So 2 pi r(h). Alright. So, curved surface of a cylinder is given by 2 pi r(h). And essentially what that is, 2 pi r is just the circumference. And essentially what we're doing is if we're unwrapping this circumference and we're stretching it out, that would be the circumference stretched out. And then if we multiply it by height, that would be, well, a square, or rather a rectangular face, and so on. And then we have the area, the curved surface of our cylinder in a sense. And that would be the area of the curved surface, is this 2 pi r(h), and it tells us just that much. Area of the curved surface is 2 pi r(h). But what about these circular bases? Well, these circular bases are given by pi r squared, and we've got one on the bottom and one on the top. So plus 2 pi r squared. That is to say, 2 circular faces as well. So the total surface area of a cylinder would be given by, well, 2 pi r(h), which is the curved surface, plus 2 pi r squared. This is pi r squared. This circular faces, and we have one on the top and one on the bottom. Okay, so that's the area of a cylinder, and they're telling us that the external surface area, which is just the surface area again, is given by this 2 pi r squared plus k over r, which looks pretty similar to this. So they said it's equal to 2 pi r squared plus k over r. 2 pi r squared plus k over r. Okay, and just actually with a little bit of rearranging, we can see that this 2 pi r squared, let's move this right here, we actually have, whoops, I didn't mean to do that, we actually have some kind of statement of equivalence. So this 2 pi r squared matches, and what they're saying is this curved surface of 2 pi r(h) should be equivalent to this k over r. What is k? To do that, we can find out what 2 pi r(h) would be. So what is the curved surface? Both of these are talking about curved surface, but one is given by 2 pi r(h), and this itself should be equal to 2 pi r(h). But, well, what is the k value once we find those missing values for r and h? Okay, so what do we know? These two things are equivalent, so 2 pi r(h) is equal to k over r. Okay, so what is h? If we can write this just in terms of r, then we'll have two equations just in terms of r, and we should be good. So let's go ahead and find out what h is, or what h is at least in terms of r. And to do that, I hope this isn't maybe going too off in terms of the process is convoluted, but remember a good IB question often asks us to make use of what has come previously. And in this first 1-mark question, especially a 1-mark question, they had us relate volume to the curved surface. This volume related to pi r squared times h. They gave us the volume, and we related it to pi r squared times h. And just with a little bit of algebraic rearranging, we can write this, divide both sides by divide both of these sides by pi r squared, by pi r squared. These will cancel out, and we'll be left with h is equal to 600 over pi r squared, or rearranging the same thing exactly, 600 over pi r squared. And so we've got h in terms of, well, r, I suppose we could say. And so if h is equal to 600 over pi r squared, wherever we see an h, like right here, we should be able to substitute. Let's do that. 2 pi r, and we said h was equal to 600 over pi r squared. So 600 over pi r squared, make that a little clearer, pi r squared, and this is all equal to k over r. This is going to take a little bit of algebraic simplification. 2 pi r squared, remember we're multiplying two things, we're essentially multiplying this by this. 2 pi r squared is the same as 2 pi r squared over 1. Remember multiplication rules, we just multiply, when we're dealing with fractions, multiply the tops and the bottom. And we can rearrange. We have an r on, actually, should we do this? Actually, yes, I'm going to. Let's multiply our plain numbers together. 2 times 600 is 1200. Pi just stays by itself, and then r stays by itself. On the bottom, the denominator, we have pi r squared, and this is equal to k over r. Let's look at this equation right here. We have a pi in the top and the bottom. We can cancel out. We have an r in the top, and then there's r times r squared in the bottom. So we actually get rid of one of those r's. What we have here, I'm going to, just because I'm running out of space, I'm going to say this. What's the next step? We essentially have 1,200. That's this part, because the pi and the r canceled out. 1,200 over r, which is equal to k over r. And these two things are equivalent to one another. That is to say, this is equal to this. And if that really is the case, then what must k be? If these things are a mirror image of one another, what must k be? Well, k has to be that missing piece. K itself has to equal 1200. If these things are mirror images of one another, then k itself has to be equal to 1200. And that is the answer. K is equal to 1200. So let's go ahead and see once again 4-mark question in terms of process marks, setting up a statement of equivalence, finding h in terms of r by drawing on what came first through this algebraic simplification, substituting, simplifying, and then showing an equivalence. Okay, good question. A little heavy on the algebraic manipulation potentially, maybe not, but not a bad question. Alright, find the value of k, did that, and now we're on to this part. Find dA over dr. Find the change in area as a function of the change in radius. Okay, so I'm actually going to work this out down here. So here's our function. It's a is equal to 2 pi r squared plus, we found out what k was, so let's write that out as 1200 over r. Okay. And they're asking us to find dA dr. Usually we have something like this. So we'll have like y is equal to, this is, let's just say, I don't know, 3x squared plus 4x, something like that. And we want dy dx, change in y over change in x. And what we do is we take the derivative in regards to, I guess, this x variable, or I guess this is the variable which we differentiate with respect to. And the same way here, if we have dA dr, we differentiate with respect to r. That is to say, r is the variable that we're going to be concerned with, just like in dy dx, x was the variable we're going to be concerned with. And so if we look at this, here's our r squared that we're going to have to differentiate with respect to. And we might say, oh, well, what about this pi? Remember, pi itself is just a number. Pi is 3.14. It's a constant, and it doesn't change. So in a sense, if we imagine this is 3.14, this is like 6.28 is sitting in front of this r squared. This r and this r is the only thing we really need to be worried with, because these are the variables that we're differentiating with respect to. This is just a constant, and we leave it as it is. So let's go ahead and differentiate. So we want to find dA over dr, or change in a over change in r. There's one problem here. There's a variable in the denominator. Before we begin to work on this, we need to bring everything up 2 pi r squared plus, this is r to the 1, let's bring it up. This is 1200, used to be r to the 1. If we bring it up from the denominator, it now has this -1. Remember, that would be the same if it was like r cubed. Bring it up, r to the -3. And just to expand just a little, if we have 1200 over r, remember that's the same as 1200 times 1 over r. And then we know that, well, 1 over r is just r to the -1, and so on. So this is just a constant. We can work on this by itself. We can separate them and work through things that way. All right, we've got a. Now we can use the power rule, dA over dr. Remember, power rule is in the formula booklet as well, but essentially what it says is take the exponent, multiply out in front. So 2 times 2 pi r gives us 4 pi. Before we had 2 pi's, we multiplied by 2, now we have 4 pi's. And then what do we do with that exponent? We multiply it out in front, and then we reduce it. We reduce it by 1. So now it was once 2, now it's 1. Let's do the same here for the second term. -1, multiply it out in front. -1 times 1200 is -1200. R used to be -1, take 1 away from it, now it's -2. Okay, there it is. That is dA over dr. And I imagine that's about 3 marks. Usually 1 mark is recognizing that we need to represent this with a negative power, and then this coefficient being correct, and then this coefficient being correct. Okay, this is question E1. And then let's go on to part 2. All right. Given that A has a minimum value, find the value of R that will minimize the material used. Okay. So for this question, I believe if it said hence up here, then we'd have to make use of this. Since it just says given that, I think we actually have some freedom, and in that sense, we can actually take this area, graph it, see what it looks like, and then find a minimum. If it said hence, we would need to use this derivative. So I'll show you both ways, and you can see what you might prefer in some kind of sense. So imagine this is area and the radius. We can change the area, we can change the radius. We can stretch it out, make this a really, really wide radius, for example, and we might have it to the point where if we only have a limited amount of volume, if the volume itself is fixed at 6,000, then it might be in some sense a very wide can, but very, very short. Or you can imagine if we had a volume of 6,000 and the radius was super small, we'd have a really, really tall can, because we need to fit 6,000 cubic centimeters within it. We'd have a really, really tall can, but it'd be really, really skinny. Our radius would be really, really short, but the volume would be very, very, radius would be very, very small, and the volume itself would stay constant, but our height would have to change. And we could stretch out the radius as well. And it'd be very short can, I suppose. And with each of these configurations, with each change of the radius, we would be changing the overall area, the area of the, I guess, the surface area and the material, the amount of material that we would use. So here's area as a function of the radius. And just for example's sake, let's say we have something that looks like this. Something like this. I'm not sure what it might look like. In this case, what would be the minimum value? If we plot it, this would be the minimum value. But how could we use this derivative right here? Derivative, remember, gives us the instantaneous rate of change, or the slope of a line at a point. So if we're looking at any given point, we plug in a value of r, and it will tell us the slope of a line at any given point. Here, the slope of a line. Here, the slope of a line, the instantaneous rate of change. And then there comes a point where we reach a minimum. That is to say, we are done decreasing. That is to say, going down, going down, going down, going down. And there comes a point where we have a rate of change that is equal to 0. That is to say, the slope at a given point is no longer negative, like it is here and here and here and here. Now, the slope is equal to 0. Or we could say that change in area over change in radius is equal to 0. So this is this turning point. The turning point happens when we move from decreasing to increasing. Before we start increasing again, there's going to be a point where our slope is 0. And so if we want to find the minimum area, essentially what we're finding is when dA over dr is equal to 0. And this is dA over dr. So when is this 0? For what value of r is this dA over dr equal to 0? And with that, we should be able to, I was going to say we should be able to end solve, but with this being 12,000 over r squared, it's possible that we might have two solutions. So we might want to potentially graph this. All right. Okay. Let's do two things. And to be honest, actually, if we're going to graph this, then we might as well just graph the original function and find the area that way. We can do both. Maybe start by graphing the original area function and finding the value of r that minimizes it. And we can find it using this derivative as well. So let's go to the graphing calculator. I'm going to graph the original. This is 2 pi r squared. Sorry, we can't use r. This is x. We've got to use x. 2 pi x squared plus, set up a fraction, 1200 over, not r this time, but x. Okay, only partly shows up. Let's try zoom fit. Maybe that will give us some luck. Oops. Not bad, not bad. And so where is the minimum? It's a rational function, which means this x is in the denominator. It means that this will go up to infinity when x is equal to 0. This is our vertical asymptote, remember, when x is equal to 0. But it looks like it goes down, and it reaches some minimum, and we can barely see it, but it looks like it starts to increase over here to the right. And I'm going to pinch zoom, and we see it does actually start to increase. And so the question is, okay, well, where is the value that it reaches its minimum? Let's go analyze graph, and let's find the minimum value. And the minimum value occurs when r is equal to 4.57. So going to go to the document once again, and I'm going to write that out. R is equal to 4.57. If we wanted to show process in this case, then we can go ahead and model this, and then we can put this coordinate point 4.57, we might want to put 393 or 394, I guess, the 3 sig figs. And that should be fine. As long as we sketch and plot our minimum, that would be all right. If we wanted to use this derivative, I'm going to go back and go to the calculator. Here we are. What we can potentially do is solve, menu, algebra, numerical solve, and solve this derivative this way. So 4 pi, in this case we can actually use r. 4 pi r minus 1200 is going to be r to the negative 2. So this is our derivative. We say, okay, well, when is this derivative, which gives us the slope of a line? For what value of r is our instantaneous rate of change? Is our slope equal to 0? Let's go ahead and press, get this in respect to r. And there it is as well, 4.57. So in this case, both could work. Since this is a rational function, there's, I think it's risky sometimes. It's not impossible to have a rational function that will have 2 intersection points for some values, especially if this is wildly different. Then I think potentially it's a little risky. But I think graphing might be the better option, but in this case we can set it equal to 0, the derivative equal to 0, and then solve. Okay, let's go on. This is part F. The containers are made so that the surface area is minimized. So that means when our r value is equal to 4.57. So we've minimized the area. This is a point where we minimize the area. The 5 centimeters by 9 centimeter rectangular, the 5 centimeter by 9 centimeter rectangular label is to be glued to the curved surface of the container. Show that the label will fit on the container. Okay. So what is going on here? So we're going to minimize, the curved surface area is minimized. Okay. And we want to ensure that the 5 by 9 centimeter rectangular label will fit on the container. So r itself is equal to 4.57. So the containers are made so that the surface area is minimized. And the surface area is minimized when r is equal to 4.57. So we've got some cylinder, and we want to put a 5 by 9 label. Okay. The surface area of a cylinder is given, once again, by 2 pi r squared plus pi r h. Okay. 2 pi r squared plus pi r h. And the 5 by 9 centimeter rectangular label is going to be glued on the curved surface. So remember, these are the 2 circular faces, and then this is the rectangular face. So we don't actually need this section right here, this 2 pi r squared, these curved surfaces. So we can actually get rid of that. And we just want to make sure that overall, this 5 by 9 centimeter rectangular label can be glued to the curved surface. So what is going on here? Let's go ahead and sketch this. Maybe that will help. So we've got this 5 by 9 label. And the radius, of our cylinder, remember when we spoke about it earlier, we said that there was some curved surface of a cylinder. And the cylinder has a radius r right here. And when we roll out this curved surface, it's equal to the circumference, which is given by 2 pi r. And so this right here was equal to 2 pi r. And this right here, this remember, or this stays the same as our h. So is this label going to fit? Well, r itself is equal to 4.57. So that means that if r is going to fit, then we want 2 pi r to be less than 9. So right now our cylindrical can is equal to, our cylindrical can is equal to 2 pi r, and we want to make sure that the label can fit. So 2 pi r needs to be greater than 9. And is that the case? Well, let's see. 2 pi r is 4.57. Is that greater than 9? I'm going to work that out on the calculator that I have here. 4.57 times 2 pi. This gives us a rather large value of 28.714, or just 28.7. And that is, of course, greater than 9. Almost great enough to, raise the question of, have I made an error actually? And just checking out the mark scheme, actually, this is correct, 28.7. But it is so much bigger that we might wonder, has there been a mistake? But no, this is the correct value. How can we ask questions about h? How can we relate h? Where did we have some indication of what h was? H, we found out, was right here. So if we know what r is, which we do, we can plug in that value and then find the corresponding h value. So I'm going to grab this actually and bring it down, and then we'll plug in for this. So h is equal to 600 over pi r squared. H itself has to be greater than 5 for this to be for this label to fit. So let's find out what h would be. Keep the colors consistent. H is equal to 600 over pi 4.57 squared. Okay. Again, I'm going to work this out on the calculator that I have beside me. 4.57 squared times pi, 600 divided by all of that. And this gives us a value of 9.1446, so on, 9.14. Okay, so we know that h itself is equal to 9.14. That's the height of our cylinder, and the label itself is only 5, so we know that 9.14 is greater than 5, and the label should fit. So these are our two justifications right here. The dimensions of the cylinder in relation to the radius and the height should cover the label. Good, nice kind of geometry question mixed with some calculus. Kind of nice question. All right, question 5, 17 mark question on a paper 2. These are usually the most challenging. Let's see what we have. Okay. Gaurica is designing a tent in the shape of a right pyramid with a regular hexagonal base. Regular hexagonal base means that all of these side lengths are equal. That's what regular means. So regular pentagon, for example, all of the side lengths are equal. Regular, any kind of polygon has all the side lengths equal. So a right pyramid with a regular hexagonal base with a center of M. The length of each side of the base is 2. The length of each sloping edge is 3.4. And the distance between each vertex on the base and M is 2. The distance between each vertex on the base and M is 2. So the midpoint, I suppose. Or at least the point at which, if we were to drop in altitude, this would be m right here. And so the distance again is m, or am is 2 right here, as shown in the diagram. Okay, pretty cool, I think. The top of the tent T will be supported by a vertical pole from M. Okay, so M is at the center, and we're going to create a vertical pole going down to the center of this tent. Kind of neat. Okay, find the length of the pole MT. MT. So, I'm actually going to zoom in a little. What we're asked to find is the length right here, essentially the height of the tent. And how can we do that? Find the length of MT. Okay, this is kind of neat. So this is our, maybe I don't actually need to zoom in so much. Maybe I won't. Here we are. So we want to find this height right here, and we're given this sloping edge, and we also know that the distance from M to B is actually equal to 2. So we know this side length is 2. And in this case, we actually know 2 out of the 3 side lengths of a right angle triangle. So just to draw that here really quick, this right angle triangle, and we know that this, where'd it go? We know that this sloping edge is equal to 3.4, and this base is equal to 2. This is a right angle triangle, and now we can actually use Pythagorean theorem. So square length of one of the smaller side lengths, square of the other side length is equal to the square of the hypotenuse. We can go ahead and end solve this, or we can write h squared is equal to 3.4 squared minus 2 squared, and then we can take the square root of all of that business. And I am going to go to the calculator and work that out. So let's go into the square root. 3.4 squared minus 2 squared, and we want the square root of all that. Of course, you could have just end solved, or we could just end solve this. And the value is 2.74955, or 2.75 to 3 sig figs. So going back to the document, MT, which is actually what it's called, is equal to 2.75. All right, not bad, not a bad start. The hexagonal base can be divided into 6 equilateral triangles. Find the area of the base. The area of the base, okay, that's a nice question. So the area of the base is going to be this whole thing, and this base itself is made up of equilateral triangles. Equilateral triangles, remember, have all 3 equal side lengths, and there's actually a song about this. 3 equal angles are hidden inside. So 3 equal side lengths, 3 equal angles. Angles of a triangle add up to 180 degrees. So if we have 1, 2, 3 equal angles, we have, well, these are all going to be 60 degrees, 60 degrees, and 60 degrees. Okay. We also know that equilateral triangles have all equal side lengths. So if this side length is 2 right here, we know that this is equal to 2, then we know that this is equal to 2, and this is equal to 2. All right, so there's more complicated ways to solve this, but I think the easiest way to potentially solve this is to recognize that these equilateral triangles are non-right angle triangles, and we've got 2 side lengths and an included angle. And in that sense, we can use the area of a triangle formula. Area of a triangle is equal to 1/2 AB sine C. This question is 5 marks. Area of the base, I believe, is only 2 marks. So, I mean, maybe some of you may be thinking, hey, can't we just create this as a right angle, say this is 1, we know this is equal to 2, find the height, and then we can use base times height over 2. You can do that, but I think that might take a little longer. I think writing this out using non-right angle trigonometry might be a little quicker, potentially. Remember, we can use the area of a triangle formula when we have two side lengths, like this, and an included angle. And that's the case, two side lengths, included angle. So let's go ahead. 1/2, in this case, side length 1 is 2, other side length of 2, sine is equal to 60 degrees. And this is going to be 2 sine 60, which is going to be root 3, which is going to be, is it going to be root 3? It is going to be root 3. That would be the area, and then multiplied by 6 would give us 6 root 3. But let's work this out, this right here. We can go to the calculator. I'm going to, well, I guess work it out on the calculator as well. 0.5 times 2 times 2 times sine 60, and this will give us the decimal value of 1.73, which is actually equal to, or sorry, an approximation of root 3. The exact value is actually root 3, but 1.73, that would be the area of one of these triangles, and we have 6 of them. So actually, you know what I should do? Sorry. We usually want to keep as many digits as possible up until the very end, and then we want to simplify or write to 3 sig figs. So if we want to use a decimal approximation, what we should do is keep more digits. So 1.7320508 or so. I think that's okay. And now, since this is equal to just one of these triangles, and we know we have 6 of them forming the base, we know the area of the base. Let me write this out here. Area of the base is equal to 6 areas of these triangles. If we wanted to write that, we could. 6 times 1.7321 is going to be equal to 10.39. And to 3 sig figs, we can write this as 10.4. Okay. There we go. Okay. Area of the base is equal to 10.4. Let's go on to the next question. The volume of the tent. Cool question. I think it is. Volume. So we might say, hey, I've never learned the volume of a right pyramid with a regular hexagonal base. If we have any kind of shape, any kind of pyramid rather, with I'm actually not even sure if it's regular, if it needs to be regular, but if you remember our cones, for example, cones, for example, the volume, and this is in the formula booklet, is 1/3 times pi r squared times height. And this is 1/3 pi r squared is area of the base times, well, the height. And with our square base pyramids, once again, we have something like this. I'm going to try to draw a square base pyramid. Something like this. I don't think that's very good. How could we draw a square base pyramid? Maybe something like this. Maybe that's a little better. This again is equal to 1/3 area of the base times height. So in this case, if we have a square base pyramid and the side length is s, it would just be s squared times height. And that would be the volume of a square base pyramid. At any time where we have a regular base, such as this, we can take 1/3 times area of the base times height. And maybe there's kind of a hint because they're asking us to find the area of the base, but that's what we can do. Volume is equal to 1/3 area of base times height. In this case, 1/3 area of the base is 10.4, and the height itself, I think we found that earlier, as 2.75. 2.75. Let's go ahead and work that out. I'm actually, again, going to work that out on the calculator that I have beside me. 10.4 times 1 over 3 times 2.75. And this will give a value of 9.533333. 9.53, and then I think the units are in meters. They are. So volume is measured in meters cubed. Okay. Good. That is not a bad question. Okay. Let's continue on. Just thinking as well, sometimes it's not a bad practice to keep all of the digits. So instead of writing 10.4 as our area of the base, if we had more sig figs, then we could be closer to the actual value of this 9.53. And potentially, since it is the subpart, this 2.75 is okay, but this 10.4, we might want it to have kept more sig figs for this final value of 9.53, so 9.533333, just because we're getting pretty close margins. We're rounding up to the 100th value here, and since it is a subpart, might actually want to keep these values. I'm just going to do it once again really quick. So I'm going to work out the value of this right here. Yeah, do it on the calculator. So we have 6 times 1.7321. This was the area of the base. And then we can multiply this by 1 over 3. So remember, area of the base times 1 over 3 times the height of 2.75. And now in this case it's, well, still 9.53. 9.53. Okay, so looks okay. Looks okay. Okay. Let's go on. In this case, we'd want to show the units. I just looked in the mark scheme as well. We need to show units in this case. So they want to see these meters cubed. Okay. Final part, you can imagine it will be a good challenge. For extra support, Gaurica decides to attach a rope with length 2.6 to the tent at a point X on the edge of AT. So right here, edge of AT, some 2.6 meter rope. The rope will be fixed to the ground at point Y such that the rope XY is straight. The rope XY is straight. Points Y, A, and B lie on a straight line. Y, A, and B all lie on a straight line. AYX is equal to 35 degrees. AYX is equal to 35 degrees. This is in the diagram, and then they give us this 2D representation as well. Find AY. Find AY. Where is, here, AY. Okay, so the length from the base of the tent up until the point on the ground where Gaurica fixes the rope. Okay, interesting question. Let's see. In this case, I am actually going to zoom in and just maybe get a finer kind of pencil. So in this case, what do we have here? We've got this side length right here. Jeez, that's loud. We've got this side length right here. We've got one angle, and we want to find this side length here. And we might say, okay, we're in the realm of non-right angle triangles. If we know angle opposite side length, and then angle opposite side length, maybe we can solve. And in this case, we want to find AY. AY is this distance right here. So what could we possibly do? What could we possibly do? What do we know? What do we know? We know that, just filling this out a little more, we know that this is, that's too skinny. We know that, for example, this right here is equal to 2.75. It's equal to 2.75. And we know that this length right here from A to M, I think it was called, is equal to 2. Okay. And we actually know the sloping edge right here as well. We know that, which is 3.4. Okay. So we should actually be able to use that. If we know 3 side lengths, we can, very nice. If this is a right angle triangle, for example, we can go ahead and we can find this theta value. And say, well, why do we want to find this theta value? Because, remember, points YAB lie on a straight line. And we know angles on a line sum to 180. So if we know theta, then we should be able to find what remains. And then, of course, if we know 2 angles, then we can find the third, and then we can go angle opposite side length, angle opposite side length, and use the sine rule. So that looks like a good approach. Let's go ahead and do that. So let's find this value of theta. We've got an opposite and an adjacent, so let's write it out here. SOHCAHTOA, remember sine, opposite over hypotenuse, and so on. We've got opposite and adjacent, and that would be TOA, this tan. Tan theta is equal to opposite over adjacent. And we can end solve this or do a little rearranging. Call this tan inverse of 2.75 over 2. And we could either end solve this or just plug this into the calculator. I'm going to again work this out on the calculator that I have beside me. 2.75 divided by 2, and then take tan inverse. This would be 53.97. So here we are. This is equal to, theta is equal to 53.9726. I think that should be enough in terms of our sig figs. Okay, so we know what theta is. So what can we do here then? Theta is equal to 53.976. And that means that, oops, I don't need that. That means that this value, you can call it beta, I suppose, is going to be whatever is left over. Since theta plus beta equal 180, we could have 180 minus, well, theta would be equal to beta. And once again, I wish I had kept some of those digits. 2.75 divided by 2. So I'm just finding this theta value once again. I'm going to take 180 minus theta, and this will get us this beta value of 126.027. Okay. And so that would be our value for beta. And what could we do after that? Let's say we want to then use the sine rule. If we know what this angle is, we know what this is. It's approximately equal to 126.027. We know what this angle is. We should therefore be able to find this, and we can call this, I guess, the uppercase beta in some ways. That should be okay. I'm going to zoom out the uppercase beta. And we know angles in a triangle sum to 180. So after we're done adding this plus this, we ask ourselves, okay, what's that missing piece, which makes 180? And in this case, I'll actually work this out on the big calculator, because it's, I guess, been a while. So 35 plus, here we go, 35 plus 126.027, that's what we have. And I guess we could end solve, but let's just take 180. That's what the total sum of the angles in a triangle. We already have 161. So what is left over? So 180 minus, and then this is where I show my lack of familiarity with this calculator in some sense. 180 minus answer, and it's 18.973. Okay, let's go back to the document and write that in. 18.973. Okay, so we now have angle, opposite side length, angle, opposite side length. This is getting a little cluttered, I know. This is what we have. We have angle. We know what this value is right here. We have angle and its opposite side length. And similarly here, this is what we want to find, this value right here, AY. And we've got an angle right here, and we've got angle and the opposite side length. So now we can, thankfully, use a sine rule. Let's use that right here. I know this looks a little messy. So we have the side length that we want to find, A, paired up with its opposite angle, and then another side length paired up with its opposite angle. So let's go ahead. A, that'll be AY. Let's keep it as A in this case. And it is opposite to sine 18.973. 973. And all of this is equal to B, which is in this case is 2.6, and it's paired up with 126.027. 2.6 over sine 126.027. Alright, now we've got just one unknown, so we can go ahead and end solve. Let's go to the calculator, menu, algebra, numerical solve, set up a fraction, call this A, could call it anything, could call it X if we wanted. 18.973 equals, get another fraction here, 2.6 over sine 126.027. And then we'll ask to solve for A. And this is the length of the side length. Make sure you're in degrees. This actually isn't too bad. It's not like otherworldly, and it, according to the diagram, it actually doesn't look too unreasonably. It's not super small, and it's halfway between 0 and 2, so it looks like a good value. Just as a rough estimate. Okay, so let's go ahead and type that in. So going back to the document, we know that AY is equal to 1.045, or to 3 sig figs, 1.05, and this would be meters. Okay. There it is. Kind of a nice question, kind of complicated question in terms of process and what would be required. Showing, I guess, how you can find this theta value by working out right-angle trigonometry, showing how we can find this missing value, and then application of the sine rule. Okay, final question. For decoration at night, Gaurica wants to fix a strip of light from point A to point Z along the rope XY. So here's point A, here's the rope XY. She wants to fix some rope along this XY value, and it's going to be at some point Z. Okay. Find the two possible values of YZ. Okay. Interesting question. What I'm going to do is zoom in to one of these once again. This time I'll do a better job of it, get a little smaller pencil, and try to explain what this question is asking. Alright, so here she is. She's got this rope, and the rope itself is equal to 0.9 meters. So she's going to fix it from A, and she's going to fix it along this line of XY. But the rope itself is only 9 meters, right? So we can't like stretch it out and put it all the way here. The rope itself is going to be equal to 9 meters. And so maybe this is 0.9. And she doesn't want it to be like, you can't extend it and stretch it. And it says the rope is supposed to be straight right here. So it can't be sagging or anything like that. And so if it was less, this would be like sagging and sagging and sagging. There's going to be another point right here, for example, maybe that's it, where it would again be 0.9 meters. And this would be 2 points, for example, where we have this rope which is 0.9 meters and it's attached to this line of XY right here. Okay, so that's what's going on. She's at point A, she's going to fix it from point A somewhere along this line of XY, and the rope is 9 meters, or sorry, 0.9 meters, and it can be straight. It can't sag, we can't stretch it. So there's going to be 2 points along this line that are going to be options. Okay. So what can we do? What can we do? So let's go ahead. I sometimes think with geometry questions, it's helpful to put in all the values that you already know and all the information that you have. In this case, we have 126 and 18.973, which to 3 sig figs is 19.0. Since we're on a different question, we're on part E from D, we can use 3 sig figs. So this is 18.97, which would sum to 19.0 degrees. And this right here was 126, and this would sum to, well, just 126. Would stay the same. 126 degrees. Okay, so we've got 3 side lengths. I think we actually found out what AY was as well in this last question, 1.05. So here we have 1.05. Okay. Interesting. So what do we know? Okay. Here we go. So essentially there are going to be 2 points along this line, Y and X, where we can fix these lights. And we want to find those 2 points. And let's deal with one hypothetical situation where this is 0.9 and we're fixing it right here. And so we're saying, okay, this right here is equal to 0.9. And what do we have? We actually have a triangle where we know one angle and we know 2 side lengths, and we want to find this missing side length right here. So essentially what we have is we have 1, 2, 3 side lengths and an angle. And that should potentially be maybe reminding you about some things, I suppose. This is our cosine rule. 3 side lengths and an angle, we can use our cosine rule, and we could solve for x. So let's go ahead and write out our cosine rule and see how we can apply it. So here's the cosine rule once again. A squared is equal to b squared plus c squared minus 2bc cos A. Remember, this side length right here matches up with this angle. So what do we have? We have this as our missing value, and we have this 35 right here, this angle 35, matching up with 0.9. So we know when we have negative 2bc cos A, this A corresponds to 35 because it's the only angle that we have that matches up with the 0.9. So let's go ahead and write 0.9 squared is equal to, well, what is b? B squared is going to be 1.05 squared plus x squared, this is side length that we don't know, minus 2 times 1.05 times x times cos, and remember we said we chose this as cos 35 because, well, this is the only angle we have and it aligns up with 0.9. We actually chose 0.9 because this was the only angle we had that was available, and this is a side length that's opposite to that angle. Alright, and so now, although it looks kind of funny, we actually have an equation with just one unknown. And we should actually be able to solve this. We should be able to solve this. Since it's a quadratic, we are actually going to have two solutions. So, we can do one of two things. We can graph this right here, and then graph 0.9 squared and find the intersection, or we can end solve and use some kind of domain restrictions. I'm a little hesitant to graph this just because it should be okay actually. I'm going to graph it and then we'll end solve it as well. So here we are, 1.05 squared plus x squared minus 2 times 1.05 times x times, whoops, this is a rather big x. There we are, x, and this is cosine 35. Okay, so this is all good. Plus x squared minus 2, 1.05x cos 35. Okay, nice. It's a great quadratic. And let's find out when it is equal to 0.9. Graph entry, this should be equal to 0.9 squared. Okay, and I'm very happy that it's come below because I was worried that an x value would be negative and suggest that something had gone terribly wrong. So there are actually two values here. What are the points? Let's find the intersections. So those two values for x that will complete this, one is 0.19 and the other value of x intersection is equal to 1.5289. So remember, this is our cosine law, where we relate the possible side lengths to each other with one angle, and this is 0.9. This is the other side of our cosine law, and we wanted to find out when these two functions were equal to one another. So going back to the document real quick, we say that x is equal to, one of those solutions was 0.19131, or 0.191, and then the other solution was 1.5289, or 1.53. Okay, so let's just go back to the question, make sure we answered it. Find two possible values of yz. And that's actually it. That is our answer in the end. So x could either be 0.191. I'm actually going to erase this and just kind of show what is going on here. So this is 0.9. Let's erase some of this and this. So we've got this. X could either be 0.191. So this is our triangle once again right here, and then it could either be 0.191, which is actually really not too far. X could be equal to 0.191, and it might be right around here, for example. That might be our, this is 0.9, not too legible, but I think you can get the idea. This is 0.9 right here, this side length, and that would be one area that we could put this, attach this rope, 0.9. And the other area that we could potentially attach this rope is all the way up at, well, maybe not that far, but all the way up at 1.53. 1.53 right here. And this would be another length where it is 0.9, and we're talking about this side length, 1.53, and then the 0.9, and we actually have two values given this angle of 35 degrees. This is one of the kind of features of the cosine law in this case, or even actually just non-right angle triangles rather. There are two possible values that would satisfy these given constraints. With two side lengths and an angle here, there are two such values. Because there are two triangles that could satisfy these constraints, I guess we could say. Alright, and I said I would actually show one more way in terms of using nsolve, and here it is. So going to the calculator screen, this was our equation once again, menu, algebra, numerical solve. It was 0.9 squared, and it was equal to 1.05 squared plus x squared minus 2, and then so on. 2 times 1.5, sorry. 2 times 1.05 once again, and then times x times cos 35. So this was our equation. This is a squared is equal to b squared plus c squared minus 2bc cos a, and we can solve for x. I believe we can. And there is our first value, 0.913. You say, okay, well, that's only one value. In this question they asked for 2. So if we highlight this once again, then press enter, we have this function once again. And in this case, this was our first value, and what nsolve does is it finds the closest value to 0. Sometimes this actually gives you a negative value. In this case, the closest answer is 0.19. And if we wanted to go above this, we can put a comma, and we can put 0.1913, or let's just put 0.192. And what this calculator is going to do next is it's going to find the next value of x that satisfies this equation with the lower bound of 0.192, so something that's greater than. And with this we can find the next one, the next solution, which is 1.528 or 1.53. Okay, so going back to the document, these are of course the two values which we found earlier. All right, and I think that's the end of this exam. Okay, so I hope it was helpful, and as always, best of luck. Take care.